Welcome back to the continued video series as we prepare for our midterm exam. This video focuses on the problems from Unit 5. We'll talk about linear programming. We'll actually do some concepts where we talk about a system of constraints and objective function, and we'll eventually get to a problem that has us do some graphs. Don't worry too much about the graphing approach as it relates to the final or to the midterm. Make sure you understand the process itself. All right, so problem 22 asks us to reference Sam. He's going to make some clocks. He's got two particular kinds that he makes. He makes pine and he makes oak. So the first thing you need to do is represent how many of each clock type he's involved in this problem. It doesn't matter which letter references which particular kind of clock, but it's important that you designate that for your problem solution. I chose to let X represent the number of pine clocks that he's going to sell, and Y represent the number of oak clocks that he's going to sell. And that's all Part A asked us to do, represent our variables. Part B says, now let's talk about what it is that you want to maximize or maybe minimize. In this context, it's a profit that we want. We're going to try to maximize this guy's profit, realizing that he makes a profit of $3 for each pine clock that he sells, and he makes a profit of $4 for each oak clock that he sells. So we'll represent his profit set at 3 times X plus 4 times Y, and that is it. So objective function simply says, in the context of your variables, what is it that you seek to maximize or minimize? In this case, it's profit. I thought P was a good letter rather than, OBJ for objective function. Part C says, let's talk about constraints. So what restrictions are there in the verbiage of the problem that affect us? So first of all, I realized that we couldn't have a negative amount of clocks. So the first two constraints, the first two of those inequalities, are going to signify the fact that we either have some pine clocks or we have none. So in both X and Y, we're excluding the possibility of negative amounts of clocks. So see, X has to be greater than or equal to 0, as does Y have to be greater than or equal to 0. The other constraints in the problem have to do with what kind of things restrict. So the restrictions in this problem are relative to how much time it takes to make each of these clocks, and how much varnish it takes to finish each of these clocks. So if you read the problem critically, it says it's going to take him 2 hours to assemble every oak, and it's going to take him 2 hours to assemble every pine. So 2 times X, where X references the number of pine clocks, would reference the amount of work required in terms of hours to make those, plus the 2 times Y, again, 2 hours for each oak clock as well. And he's only able to devote at most 20 hours. So there's your third constraint. 2X plus 2Y has to stay less than or equal to 20. The last constraint has to do with varnish required for these. And in the context of the problem, each pine clock needs 1 unit or 1 ounce of varnish, but each oak clock needs 4 ounces of varnish. And we have at most 16 ounces of varnish to use in our project. So we're going to see that our last constraint goes X plus 4 times Y. Remember, it's 4 ounces for each of those oak clocks, cannot exceed, so less than or equal to 16. And that, my friends, is our last constraint. And according to the words, that's it for problem 22. It's a setup entirely, and that's all we had to do. So we're going to move to 23. On the visualizer, 23. Again, part of the notion of linear programming. So in this case, Fred's already done the work and he's found the vertex locations for his feasible region. And they're listed as you see them, 0, 0, 11, 0, 9, 4, 5, 8, and 0, 10. And his objective function is given as 60x plus 50y, and the objective function is labeled as P equals, so maybe P for profit. All right, and the question says, determine the maximum value of this objective function. Well, what you should recall from the notions of linear program is that a maximum or a minimum value for the objective function must occur at one of your vertex points of your feasible region. So we're going to take each of these ordered pairs individually and pop in their X values and Y values into the objective function. It's plug and chug, it's arithmetic. Grab your calculator if you want to, and that's what we see on your screen. First 60 times 0 plus 50 times 0. Okay, no fake. We're going to make 0. Now it's kind of a no-brainer. 60 times 11 added to 50 times 0. That's a p-value of 660. Straight through it, 9 going in for x and 4 going in for y gets a 740. It looks so far like that might be the biggest. And I went ahead and did the others because at the moment you didn't know it was the biggest. So we'll put in 5 for x, we'll put in 8 for y, and that generates a p-value of 700. 0, 10 pops it in at 500. And again, visually, the biggest of those is 740, and the objective value then is maximized at 740, and it's maximized if we sell 9 of the x's and 4 of the y's, whatever it is they were referencing on problem 23. We don't really have that knowledge in the verbiage of the problem. Problem 23 done, maximum value at 740. Problem 24 gives you a system of constraints and an objective function and does ask you to generate a graph. All right, so I'm going to slide the graph up here and we're going to talk about it. The first of your constraints is x has to be greater than or equal to 4. That's this vertical line running 4 units to the right. So you got to be greater than that, so your shading runs relative to that line to the right. You also have to be greater than a y value of 1. So that's this horizontal line running across that 1 unit, and you've got to be greater, so you're above that. Your third constraint's relative to x again, and it's x has to be less than or equal to 8. That's the vertical line out here, 8 units to the right, and since we have to be less, the shading relative to that line runs left. The diagonal line is the last constraint at 2x plus y less than or equal to 18. I went ahead and solved for y, got me a slope, got me a y-intercept. Then I realized that intercept's not very nice on this particular graph. You know, I didn't have a high enough thing to show you 18 well. So I did a t-chart. I selected some x's. I'm not going to lie to you. I cheated. I knew those vertical lines at 4 and 8 were going to be significant. So I picked x at 4 and I picked x at 8 because I figured they were going to help. Put 4 in for x and you find out that y becomes 10. Put 8 in for x and you find out that y becomes 2. And you'll see that there are 2 bold dots on that graph, one at 410 and one at 8.2. And then I simply grabbed my trusty ruler and drew that straight line. And we had to be less than, so that shading goes down relative to that diagonal line. Feasible region sets up and you can find your vertex locations. I listed them for us. Again, in no particular order. We got 4.1, we got 8.1. Looks like we have 8.2, and it looks like we have 4.10. So those are my endpoints, my vertex points for my feasible region. For us to go ahead and find maximum value, we're going to take those values and run them into the objective function. All right, if you remember, the objective function was 5x plus 10y. I probably should have written it there, but that's what's going in. And you're substituting the x's and the y's into that function. So for the ordered pair 4.1, it's 5 times 4, 10 times 1, gets you a value of 30. For 8.1, it's 5 times 8, 10 times 1, gets you a value of 50. For 8.2, you're going to throw in and get 60, and it looks like the maximum is going to exist when x is 4 and y is 10. And according to Dell's calculation, that's a value of 120. So the last entry you see on your screen is we maximize our objective function, and it has a maximum value of 120, specifically when x is 4 and y is 10. And that wraps our 24 solution as it relates to a linear programming problem where we did get a chance to go ahead and draw the graph. Not too bad. We should be okay there. And I do believe that will wrap us through Unit 5. I'll be back soon with a look at the problems from Unit 6. We'll see you then.